Welcome to this movie on statistical mechanics. My name is Jos Thijssen and I teach statistical mechanics for the Master in Applied Physics students at the Delft University of Technology. In this movie I want to solve the one-dimensional Ising model exactly using the transfer matrix method. That is a very important method when people try to solve statistical models exactly, and solving a model means solving the partition function. However, the solution also gives us insight in the correlation function and which values it may assume, and we will find that a one-dimensional model, for example, cannot exhibit a critical phase transition. And in the end I will comment on the relation between statistical and quantum mechanics, and the transfer matrix formalism is a key in establishing that relation. I consider the Ising model in one dimension, and the Ising model in one dimension is just a chain of spins. So we have sites at regular distances, and the sites are labeled by their index I, and at each site I there is a spin which can either be up or down. That's typical for the Ising model, which allows only two states, up or down. The Hamiltonian favors like spin in the case that where the coupling constant is positive, so the spins like to be both plus on the nearest neighbor links or both minus. The energy will be higher when the spins are different, and there is a magnetic field which favors one type of spin. And the partition function can easily be written down. It is given by this expression where I have used a particular notation. J is the same as beta k, so that's k divided by kbt, and the B that contains the magnetic field, little h, and so this is h divided by kbt. So this is my partition function. Here is my Hamiltonian multiplied by minus beta, and I have to sum over all the possible configurations of pluses and minuses along the chain. Now I can rewrite this as follows. First of all, I see that there is a sum over I in both terms in the Hamiltonian, and I can put that sum in front of the exponent, and then it turns into a product. So I now have a product over I. Now a second change I have implemented here is that here I have one B field per site, and here I have a B field coupling to Si and to Si plus 1, and then I divide by 2. So I can either take the magnetic field for this one, for that one, for that one, for that one, add them all up. That's this form. Or I can put for each link, I take half of this spin and half of that spin, and then for the next link I again take half of this spin and half of the next spin. And because there are periodic boundary conditions, that doesn't matter, but it gives me the advantage that this is now a symmetric expression in Si and Si plus 1. So the next step, I'm going to introduce a new object which will give me this Boltzmann factor here, this Boltzmann weight. And that new object is called a transfer matrix. In fact, the Si and the Si plus 1, they both can assume the values plus or minus, and I can write those as vectors, a vector 1, 0 or a vector 0, 1. And if I write those as vectors, then I can write this as a matrix element of the operator T just taken between those two vectors Si and Si plus 1. They assume the values plus or minus, where plus is identified with this vector and minus with that vector. So if I want to fill the matrix T according to this, then I start with plus plus. So the Si and the Si plus 1 are both plus, so I get an e to the power j here. And here I get a plus b, because both Si and Si plus 1 are plus 1, so they add up to 2, and so I get a plus b. In the lower right corner, I have 2 minus spins, so I again have an e to the power plus j, and then this term gives me now a minus b. And if Si is 1 and Si plus 1 is minus 1, then I'm here. Then I have an e to the power minus j, and this term vanishes because one of the s's is plus and the other one is minus, and here I have the same. So this is the explicit form of that matrix, but I won't use that anymore. It just because you can perform this trick for any one-dimensional model. It doesn't have to be the Ising model. So I can always write the partition sum as a trace over some spin variables, whatever they may be, and then a product over the links of the letters, and then I can define for those links the transfer matrix, which just couples one side to the next. So let us put that into this expression. We have a product of all these matrix elements. So I have an S1, S2 matrix element, and then the next one is an S2, S3 matrix element, etc. And I have to sum over the possibilities where S1 is plus or minus, where S2 is plus or minus, where S3 is plus or minus. And then using the completeness relation from quantum mechanics, I note that wherever I have an S and an S like this, cat vector, bra vector, and I sum over those S's, then I can replace that by the unit operator. And so all these terms here, they disappear because they are unit operators. And that means that I get a whole lot of T's multiplied by each other. In total I get n of those. And then I'm only left with the first and the last spin, the S1. And I have to sum over the two values that S1 can assume. S1 is plus or minus. So this is the result. I have the matrix element of t to the power n, this operator raised to the power n, between S1, S1, that's a diagonal matrix element, and I have to sum over these diagonal matrix elements. And if we sum the diagonal elements of a matrix, we have a notation for that. It's called the trace. So this is called a trace. Trace is just the sum over the diagonal matrix elements. In order to make progress, we assume that we can diagonalize T. So we have the operator T, it acts on an eigenvector, and then we have the eigenvalue multiplied by that eigenvalue vector. And we assume always that the eigenvectors, that they are properly normalized. And so let us write out now the trace of T to the power n. Well, the trace is independent of which basis we use. It's always the sum of the diagonal elements. And we can, instead of the S1, which we had here, we can also use a basis consisting of eigenvectors, the phi n's. And if there is an eigenvector here, phi n, then the t to the power n is replaced by lambda n, also raised to the power n. And the phi n gives me a 1, so I just get the sum over n of lambda n to the power capital N, which is the length of the chain. Now we are interested in the thermodynamic limit, so we take n large. And now assume that there is one eigenvalue which is larger than all the others. And it only has to be a few percent larger than the next eigenvalue. If this n is really large, then the largest eigenvalue in the absolute value will dominate all the others. So the conclusion is that if the n is large enough, there is only one term left from this sum, and that's the maximum eigenvalue of this matrix. And that has to be raised to the power n. Now, to be specific, in the case of the Ising model, where we have a 2 by 2 matrix, you can do an effort and try to diagonalize that matrix. You will find two eigenvalues, and those eigenvalues in general are different in value. So I just take the largest of those two eigenvalues and I raise that to the power n. The n, and I should perhaps remind you of that, it's the length of the chain, and we assume that to be large. So the little n only runs over the dimension of the transfer matrix, which is the same as the number of allowed spin values, and this capital N, that is the length of the chain. So that means that if I diagonalize this matrix, I have, in fact, what did I calculate? I calculated the partition function. I started with the partition function, and then I concluded that that partition function is the same as the trace of t to the power n, and then we have seen that the trace of t to the power n is just the maximum eigenvalue to the power n. So if I can find the largest eigenvalue of the transfer matrix, I'm done. I know what the transfer matrix is. However, it is very instructive to consider another object that I can calculate with the transfer matrix, and that is the correlation function gjk. So what is the meaning of the correlation function? Well, as you can see, it contains some expectation values. First, it is interesting to look at the expectation value of a single spin. So if on average there is a majority spin, for example if there is a magnetic field which favors the upspins, we assume that if I am at a particular site and the spin is flipping there between plus and minus, I will see more pluses than minuses if the pluses are helped by the magnetic field. And so this would have a non-zero expectation value. I can do the same for k, but because my chain is translationally invariant because of the periodic boundary conditions, I expect these to be the same. They are both just the average magnetization, so this will be m and that will be m. Now, what about this? Will that also be m squared? Well, if the Sj and Sk are really far apart, they are independent, so then I would expect this value to be m squared. However, if j and k are closed, and we are interested in the following limit, obviously 1, we take that smaller than j minus k, but we take j minus k a lot smaller than the length of the chain. So if I have my chain here, it's very long, and j and k, they are relatively close. Now if I, for example, have a plus spin at site j and I measure the spin at k, it will probably be more often plus than when this spin would be minus. So these spins are not completely independent, they are correlated, and that's expressed therefore by this function jk. It tells you what the value of the product Sj Sk is in excess to the value that that product would have if j and k would be far apart and therefore uncorrelated. So that is an interesting object, this g of jk, and here you see a sketch of g of jk as a function of j minus k, and for large distances it will always decay to 0, because if Sj is really very far from k, then we expect this product to have the same expectation value as the product of these expectation values, and then the g will decay to 0. So that happens for long distances. So what do we expect for short distances? We expect to decay, and the generic form of most decay functions is e to the power minus r over xi. So we shall see whether that is the case for the Ising model too. So now the question is, how can we do this calculation? Well, in order to make progress, let's first evaluate the expectation value of a single spin at site j. We will need that in a second, so it's important to look at that. So we proceed exactly along the same lines as before. So we have the partition function, which we write now in the form trace of t to the n in the denominator. And then in the numerator, we work everything out exactly in the same way as before, except there is something extra. There is a Sj at position j, which has been squeezed into these matrix, in between these matrix elements. And now we make the following step. Let us now invent another operator S, which acting on this Sj gives me Sj times Sj. Well, so what would be the form of this operator S with respect to the basis of the up and down spins? Well, it's not hard to guess. For the plus case, I get a 1. Otherwise, these the row and the column vector are facing each other; they are perpendicular. And in the minus minus, I have a -1. So it's just a Pauli matrix, a Pauli spin matrix SZ, and that tells me that precisely gives me in the right way this extra spin. And so what I can then do is I can replace this spin by an operator S, which I squeeze in here. And then concatenating all these t's here, I'm left with only two sums in the end. There is of course the sum over the first and last spin, that's S1, and then I have a sum over the Sj, and then first I have JT matrices for the first J matrix elements here. First there is this S1, and then I have this Sj, and I have squeezed this operator now in between the expectation value, so that is now here present before this get factor Sj. And then the rest is simple, it's Sj, and then I had n minus j t vectors, t operators left, and then I end with my S1. Now we need two ingredients. First of all, the trace is cyclic. With a cyclic permutation of the operators in a trace, the trace is invariant. So what I can do is I can take these and uncyclically move them to the front, and that means that I get all my t's in the beginning of the trace expectation, because after all, here is the S1, so I have again an operator of which I take the trace. And so it's a product of many operators, and I can put those operators in front of this expression, because that's a cyclic permutation of the operators. Now the second step is that we can write each t by its eigenvalue expansion. So any operator, after I have diagonalized it, I can write it in this form. And because I have many t's here, it makes sense to keep only the largest eigenvalue, and I use now the notation where phi 0 or lambda 0 is the largest eigenvalue. And so if there are many t's, I can replace this by lambda 0, phi 0, 0. So for one matrix as it is written here, this is generally not correct, but if I know that this is part of a long sequence of t's, then I can just assume that only the phi 0, the eigenvector corresponding to the largest eigenvalue, is projected out. So in the end I see, using the fact that I sum over the Sj, so this is a unit operator again, I move all these t's in front, and then I get just a t to the power n and then a phi s. Then if I use this projection property, then t to the power n obviously can be written as follows, because everything is diagonal. And then I replace t by this expression, and then working out this trace, it can be easily seen that this gives me phi 0 operator s phi 0, and there is of course a lambda 0 to the power n, but that cancels against the same object in the denominator. And so what I do is I diagonalize the transfer matrix T. I find two eigenvectors and two eigenvalues. I identify the largest eigenvalue, and I take that eigenvector corresponding to that largest eigenvalue, and then I sandwich this operator, which is the Pauli spin matrix, SZ, between the two eigenvectors, and that gives me the expectation value of Sj. So let's go back to the definition of the correlation function, which had indeed two expectation values, and we know now how we can evaluate those two. But there is one more to be evaluated, and that's this product here. So using the same approach as we did for evaluating the expectation value of a single spin, we obtain the following. So we consider Sj as k, and so we first have jt matrices, the first part of the spin, then this is my Sj, this is my Sk, and there are k minus jt operators in between, and then there is a t in the power n minus k. And so the first choice I make is to replace everywhere the t by this expression here, phi 0 lambda 0 to the power the number of t's I have, and then phi 0. So first I had j of those t's, so that's this part. Okay, that's t in the power j. Then I have here my Sj. Here I have my t in the power k minus j. That's what I have there. Then I have another s at side k. And then, oops, I have here n minus k t operators left. So that's what I can do. Then I can, of course, I see how many lambda zeros do I have. I have j plus k minus j, that's k plus n minus k, so I have lambda 0 to the power n, and that cancels against the denominator. And the only terms that are left are the expectation value of phi 0 s phi 0 times phi 0 s phi 0, and therefore this expression here can be written as phi 0 s phi 0 squared. Now the point is that our gjk, this is the term we are evaluating now, and I should subtract these two. But we have seen that both of these have the form phi 0 s phi 0. So the first term here of this term, the first term in working out this expectation value, cancels against the expectation value of spin j times the expectation value of spin k. So this will give a 0. So this term is cancelled by this term. Well, then we should consider what the next term is, which is contributing to the expectation value. And because the k minus j is a lot smaller than n, I have only, remember this picture where I had my chain, and here is my j and here is my k. So this is the shortest distance. So here I can afford to take not the largest eigenvalue, because that's cancelled. I take the next largest eigenvalue, which is lambda 1. And then you obtain this expression. And then you see that what's left over is precisely the phi 0, phi 1 s expectation value. Now these j lambdas are cancelled by lambda zeros in the denominator. These n minus k lambda zeros are also cancelled, and what is not cancelled is the lambda 1, which occurs k minus j times, and in the denominator then I have instead of that k minus j lambda zeros. So in total I have lambda 1 over lambda 0 k minus j, and that is multiplied then by this matrix element squared, and that is then the absolute value, because this is the Hermitian conjugate of this, the conjugate of this one. And now, because the lambda 1 is strictly smaller than lambda 0, we can write this in the form e to the power minus k minus j over xi. So we see here a confirmation of the fact that the correlation function shows an exponential decay. So lambda is the largest eigenvector, lambda 1 is the next largest eigenvalue, and if we make a cartoon, then we see that evaluating the partition function we have here, we can either, but then we take lambda max everywhere. If we take the correlation function between side j and k, then the first non-zero contribution is the one where we use here the second eigenvalue instead of the largest eigenvalue. Now obviously there may be a problem if there is not a single largest eigenvalue. There may be more largest eigenvalues. So if we approach the value of lambda 0 with our lambda 1, so if lambda 1 really is getting very close to lambda 1, then the correlation length, that's this xi here, that's typically the length over which we see the decay, gets larger and larger and larger and larger. And so when lambda 1 finally hits the value of lambda 0, then this correlation length diverges. It turns out that that is typically what happens at the critical point. So, can the eigenvalue be degenerate or not? Well, there is a very important theorem in linear algebra, which is called the Perron-Frobenius theorem, and it is a theorem which applies to positive matrices. So we have a matrix A which has matrix elements Aij, and all these matrix elements are positive. Is that the case in our example? Well, that is indeed the case, as you can see here, and it's generally the case because the matrix elements of the transfer matrix are always Boltzmann weights. Boltzmann weights are exponents of real numbers, and therefore they are always positive. So our transfer matrix is a positive matrix, and it should therefore satisfy the Perron-Frobenius theorem. And that says a lot, but the most important for us now is that the largest eigenvalue in absolute value of A is non-degenerate, i.e. the second largest divided by the largest eigenvector is strictly smaller than 0, and therefore the correlation length is finite. Well, I indicated already, and in another movie I will come back to this, I indicated already that xi, the divergence of xi, means that the system has a phase transition, a critical phase transition. And therefore, for a 1D system with a finite number of states, this matrix is a finite matrix, and the Perron-Frobenius theorem should apply, and therefore the correlation length is always finite, and therefore a one-dimensional system does not exhibit a phase transition. So is there a way we can understand that? Well, it turns out that there is indeed a way for the one-dimensional Ising chain. So the one-dimensional Ising chain, it is in a phase which is defined by the minimum of the free energy, which is defined as the energy minus T times the entropy. So let us first consider all the spins being plus, and you can also choose them all being minus. That is only one phase, So there was no leeway to modify the system. So there was only one configuration, and that configuration has an energy of minus nk, that's the bare coupling constant without 1 over kBt, and that is because there are no domain walls. I just have minus nk. So that's very favorable for the energy, and the entropy in this case doesn't lower it further because the entropy is ln times the number of possibilities, but there is only one possibility and ln1 is 0, so the energy is just, the free energy is just minus nk. Now let us cut a bond. Well, there's no possibility to cut a single bond because the system has periodic boundary conditions, so I have to cut it always, I have to cut out the bonds at 2 positions. So a bond cut means that I'm having a bond where the spins are opposite on both sides. So I can go from plus region to a minus region, and then I should go back to a plus region because of the periodic boundary conditions. How many ways are there to do that? Well, omega is n times n minus 1 over 2, because I can choose the first cut at n's bonds, and then I have n minus 1 possibilities over for the left for the next one, and I have to divide by 2 in order to avoid double counting. And so if I then look at the energy, I have cut 2 bonds, and it costs me an energy of, in fact, 4k, because there are 2 bonds that go from minus k to plus k, so in total that gives me a difference of 4k. And if you consider the entropy effect, so approximately for large n, we can replace this by n squared over 2, and we see that this term will always win from the energy cost of 4k. So this is always more stable than the plus phase. And if we look at the magnetization in the plus phase, everything is plus. In this case, on average, because these bonds are placed wherever we want, there is no magnetization, and so we see that the phase without any magnetization is more stable than the phase which has a definite magnetization. And so at any finite energy, if the chain is long enough, this phase will be more stable. And so so the reason is in fact that I only need a finite amount of energy to completely annihilate a positive magnetization. That's the reason why there is no phase transition in a one-dimensional system which has a finite number of degrees of freedom per site. In a two-dimensional system, however, the situation is different. So if I have a two-dimensional Ising grid, of which I've shown here 2 columns, then the transfer matrix couples this column, which I denote by S, but it represents in fact a whole column of spin values, S1, S2, etc. So this is S1, S2, to the capital S primed, so this is S1 primed, S2 primed, etc. And the transfer matrix tells me exactly how these 2 couple. And we know that in 2 dimensions there is a phase transition, and the reason that there is a phase transition and that it's not in contradiction with the Perron-Frobenius theorem is that the matrix now is an infinite matrix, because the columns in the thermodynamic limit, the lattice becomes infinitely large, and so the columns become infinitely large, and there are here 2 to the power n possibilities for the spin S and 2 to the power n possibilities for the column of S primed spins, and therefore this matrix becomes infinitely large, and the Perron-Frobenius theorem pertains only to matrices of finite size. To conclude, I would like to comment on the relation between quantum mechanics and statistical mechanics. So as we have seen, quite generally I can define a transfer matrix which couples, for example, two spins on a one-dimensional model, or it can couple two rows of spins in a two-dimensional model defined on a lattice. And this T can be written in the form of e to the power minus beta h, because all its elements are positive, and if T is a symmetric matrix, then this Hamiltonian is also a symmetric matrix. More generally, it's an emission matrix. And so we call this H the Hamiltonian. So it's just a formal trick to write the transfer matrix as the Hamiltonian. Now this object here, it can be viewed as a quantum Boltzmann factor, like quantum density matrix, but it's a slightly different object because it only describes, for example, in a two-dimensional model, the couplings between the spins in two adjacent rows. So the H takes care of the couplings in each row and the coupling between the two rows, and so it can hardly be viewed as a density matrix of the entire model. So it's a different object. However, this notation reminds us of something else. If we solve the Schrödinger equation for such a Hamiltonian, we obtain IH ddt, and now I take the time-dependent Schrödinger equation, psi, and that is H times psi, and this is solved by this solution. So if we put this solution back into this equation, then we see that IH bar d dt of psi of t is h, and then the 1 over h bar cancels against this h bar, and then we have a psi of t. So this is easily checked. And this, of course, resembles this quite a bit, provided we interpret the beta as an I times t. So if we make the time imaginary, we can view it as a temperature. If we view the temperature as imaginary, we can view it as a time. And indeed, this is a very fruitful correspondence, especially instead of finding the largest eigenvalue of t, so instead of finding the maximum eigenvalue of t, we could equivalently find the lowest eigenvalue of h.